classifying critical points. This one I think has multiple critical points, but let's find out. So here's our function of two variables, x cubed minus y cubed plus 3xy. Here are our partials again. 3x squared plus 3y equal to 0. Fy is negative 3x squared plus 3x equal to 0. And then our second partials are fxx is 6y, or 6x, fyy is negative 6y, and fxy derivative of this is 3, or fyx also 3. Should be the same. And again, we use the two first derivatives, the partial with respect to x and with y, to solve for the critical points. So we set this equal to 0, and then we solve for x and y. So the thing is, clearly you can look at this and see that 0, 0 is a critical point, because we set x equals 0, y equals 0, this equation equals 0, and this equation equals 0, right? It's a point for both of them. But it's not obvious what else is like, right? You could guess it would be wrong, but you could guess x equal to 2 and y equal to negative 4. Because then you have 3 times 4 here is 12, and 3 times negative 4 is negative 12. But here it wouldn't work, because if y was negative 12, this would be super big, or negative, this would not be possible. So we have to solve them simultaneously. And to do that, I'm going to solve this for y. So I'm going to say, okay, 3y equals negative 3x squared, so y equals negative x squared. And then this one, I get 3x equal to positive 3y squared, so x equals y squared. And then we plug in one of these into the other one. Let's take this one and substitute it in for y right there. So I'm going to get, let's see, x equal to negative x squared squared. So x equals positive x to the fourth. This is actually very much the same equation we saw in the previous problem. So here we get 0 equal to x to the fourth minus x. 0 equals x times x cubed minus 1. So our solutions are x equal to 0 and x equal to 1. The difference between this equation and the previous one is here 0 isn't undefined. So here if x equals 0, so looking up here, if x equals 0, we also get y equal to negative 0 squared, which is going to be y equal to 0. And if x equals 1, we get y equal to negative 1 squared is negative 1, right? So you're squaring first and negating after. And those both work, right? If you plug in 1 for x and negative 1 for y, here you get 3 plus negative 3 is 0. Here you get negative 3 plus 3 is 0. Awesome. And then we're going to test them. So, again, we're going to find the determinant of the Hessian, capital D, fxx, fyy, minus fxy squared. Let's see, and so fxx, so we're just going to take this, right? 6x times negative 6y minus 3 squared. So that's going to be negative 36xy minus 9. So plugging in 0, 0, which you can write this way or with the vertical line for evaluation, you're going to get 0 minus 9, which is negative. So 0, 0 is a saddle. Plugging in 1, negative 1, you get, let's see, negative 36 times 1 times negative 1 is positive 36 minus 9, which is positive. So that means since the derivative is positive, sorry, not the derivative, since the determinant of the Hessian is positive, it's either a max or a min. We look back at the second partials, and we see that fxx is positive, fyy is also positive, so we end up getting a, minimum, right? Because positive second derivative means concave up. So we see the right fxx at 1, negative 1 is equal to 6 times 1, which is positive, which means we have a minimum at 1, negative 1. All right.